It's 11:15 now. I think we can begin the session. Hello everyone, and welcome to today's session. Before we begin, I'll briefly introduce our club and our vision. We, the Internet of Things community, IoThinC in short, are a student-run technical club at the Vellore Institute of Technology. We strive to teach and help students acquire new skills in an era of rapidly evolving technology. The mission of the club is to expose students to challenges and new advancements in the field of IoT and thus to nurture and develop their skill set in this arena. We aim to increase awareness of the opportunities presented by IoT as a growing concept, to provide a social platform for IoT enthusiasts, to network and connect with experts within the field, and to encourage students to incorporate skills into projects that they will strive to create. Today, pursuing this vision, we bring to you a webinar on generative adversarial networks using Pytorch. I would like to introduce today's presenter, Mr. Sachin Wani, currently an alpha tester at the famed artificial house deeplearning.ai. He is pursuing his master's in deep learning at the University of Florida, USA. He completed his BTech in NIT Raipur and is a JN Tata Scholar. He is experienced with deep learning aspects like CNNs, NLPs, and other deep neural networks, one of which you will be learning today. Before handing the platform over to Sir, we would like to let you know that the session is open to doubts. Mr. Wani will be taking any questions that you may have in the chat box that Google Meet provides. A recorded version of this webinar will be available soon on our YouTube channel. Its link and our other social handles are visible on the screen now. We would love to hear back from you. For those of you just joining us, welcome to this session. Sir, you can take over now.
Sure. So thank you for introducing. So hello everyone and welcome to this event. I am Sachin Wani and I'll be your speaker for today. So good morning or good evening, depending on where you're watching this from. I will start with a presentation explaining the details of deep learning and we'll start with the basics of GANs. And then we will switch to a hands-on lab that you guys can follow live and you can do it yourself. So without further ado, let's get into it. I'll start presenting my screen and we will start with the presentation first. So for today's topic, it's about the introduction to deep learning, and we will be developing a model using generative adversarial networks. So since they have already told you about me, so I'll just explain this briefly. I'm an alpha tester and mentor at deeplearning.ai, which is a company that produces courses as well as specializations for Coursera. I am a student at University of Florida, currently doing my master's in computer and information sciences with specialization in deep learning. I've completed my BTech in CSE from NIT Raipur, and I am enthusiastic about new technologies just like you guys. So, why are we learning about GANs? So, this person, Jan LeCun, is one of the founding fathers of deep learning. And according to him, GANs are one of the things that has been the most interesting idea in the last 10 years of machine learning. And as we will see throughout this presentation, as well as on the hands-on lab, you will see the various applications of GANs and why this thing, the generative adversarial networks, is hailed as one of the greatest things that the deep learning community has invented. So we will start with an introduction about what is deep learning and what is GANs. Then there will be the presentation about the explanation of GANs and all its inner working so that you will understand what GANs do and how it works before we move on to the hands-on lab where we will be going through the code for implementing GANs. And finally, you guys can also put your questions in the chat box, but finally we can have a Q&A session where I will be answering your doubt once the hands-on lab ends. So let's get into it with the introduction to deep learning with GANs. So basically, first thing that I would like to differentiate is that machine learning and deep learning are kind of subset. That it is a deep learning is a subset of machine learning. Machine learning is basically involved with the artificial intelligence, and it is basically creating algorithms that can change themselves without human intervention. So what it is basically a kind of a computer where you put in the inputs as well as the outputs that you want, and the code or the algorithm that you want is basically the output of those computers. So machine learning is not only dealing with neural networks and other things, but it also involves some heavy mathematics as well as naive Bayes classifiers, decision trees, random forest, and so on. Deep learning is a subset of machine learning that is absolutely just involved in using the artificial neural networks for most of the work. So you can say that deep learning is basically a subset of machine learning, and machine learning is a subset of artificial intelligence. So artificial neural networks that are used in deep learning can look like this. This may seem intimidating at first, but it's basically that, for example, let's say one of the most basic artificial neural networks we can use uh, is for predicting certain properties, we can say. So the input layer here are basically values that we input to the activation units here. So all of these x1, x2, x3, and xm are basically inputs to the neural network, and it passes on through these lines, which are basically weights, through the various hidden layers, and finally everything is computed and given out through the output layer. So this might seem a bit intimidating at first, but I have a GIF that I can use so that I can explain it better how it works. But as you can see that as those lines contains basically some kind of values which are basically summed up using this multiplication, and a final bias term is added to it, so that the inputs x1 is multiplied by w1, x2 is multiplied by w2, and so on till xn is multiplied by wn, and finally b is added to it, so that we get this summation. And a activation function called as f is applied to it, so that we can break the linearity. Since this is a linear function, to break the linearity we apply some kind of activation function. So I think that you guys might know about some of the activation functions, but one of the most famous, few of the most famous activation functions are mentioned here, that are this linear function that whatever you input, the output is the same, that f of x equals to x kind of thing. This is a sigmoid function which is basically used in binary classification, where the output is always constrained between 0 to 1. So for positive values, mostly the answer is closer towards 1, and for negative values, the answer is closer towards 0. The same with hyperbolic tangent function, but instead of limiting it from 0 to 1, this time we limit it from 1 to -1. And there's this really great leaky ReLU, which is basically rectified linear unit, which is basically f of y is equals to y for positive values, and for negative values, it is just a smaller slope. So this is used to break the linearity of the function so that the neural networks through its weights can learn itself. And we can use this GIF as a representation of how it works. So we can see here how the image is basically 28 cross 28 pixels, so that it is total of 784 inputs, which are going through the first input layer, passing it on to the next layer and the next hidden layer, and then finally the value which it is can be recognized. So this is one of the basic convolutional networks, or sorry, one of the basic artificial neural networks, where you take these pixel values, you input it through the artificial neural network, and you get the classification. Since there are 10 possible digits, it is called as a multi-class classification, where the final output is based on whatever is the maximum output of this. So since the 7 value is lit, we can say that the image or the input was a photo of digit 7. So that was a brief introduction about deep learning. I'll just check if you guys have any doubts, and I'll just start presenting once again. So if you guys have any doubts, you can put it on the chat box, or else I will continue. Do you want me to go deeper into the deep learning aspects about artificial neural networks, or can we begin with GANs?
Basic
No, so you can begin with GANs.
introduction would be good.
So let's continue and start learning about generative adversarial networks. So what does GANs do? So the main focus for this generative adversarial network is to generate data from scratch. Mostly GANs are used for image generation or video generation, but other domains including music has been done. So the name generative adversarial networks is basically that there are two things that are trained separately so that they work adversarially, like they are an enemy of each other. And there's this beautiful explanation given by Ian Goodfellow. He is the one who basically invented GANs. So he said that rather than training a single neural network to recognize pictures, researchers trained two competing networks, where you can think of this like being a competition between the counterfeiters and the police. The counterfeiters in this case are called as the generators, and the police is basically the discriminator, so that the counterfeiters want to make fake money and have it look real, and the police wants you to look at any particular bill and determine if it's fake. So this sentence might be a bit confusing right now, but as we soon see through this presentation, it will be more clear. So, like I said, there are basically two main components of the GANs. The generator, which is basically the counterfeiter that produces those fake images or the fake data. And there's discriminator, whose only job is to take a look at those image or the input and to say whether it is real or fake. So for generator, it takes in a certain noise and tries to generate an image in our case that is as close to real as possible. And the discriminator's job is to take the real image as well as fake image and to classify them as if it is a real image or a fake image. So for overview of GAN structures, let's say when we start the training first, for the generated data, we can see that at the beginning it can't generate good data. We can really see that this image is fake and it's not a real node. So when it is passed to the discriminator at the beginning, the discriminator can say that this image is the fake one, and we will also pass some real data, that is the real images of how the money looks, so that the discriminator can know what it has to look for. So this is the real thing. And the generator and the discriminator works in tandem such that the generator basically asks the discriminator, so what changes I can make to make my money look more real. In this case, you can say hypothetically that the discriminator says that try to add some face of a person so that it starts to look more real. And what I'm saying is that the errors that are generated are basically back propagated so that the generator gets better. So as the training progresses, the generator gets closer to producing output that can fool the discriminator. So now, from the input of the discriminator, it has started producing some digit of the denomination as well as some face, but it's still nowhere as real as the real data or real money. And the discriminator can still see that it's a fake image in this case, and the real data set, it can know that it is real. But finally, once you train it for a long time, the generator training goes well So the discriminator gets worse at telling the difference between the real and fake. And if it starts to classify the fake data as real, then we can know that the generator has done a good job. As you can see in this case, the $20 denomination bill seems pretty legit, which is generated by a generator. And since it is very close to what the real bill looks like, the discriminator can't discriminate between the two and says that those both images are real. So using a flowchart, this is basically the overview of GAN structure. The main part of this thing is the discriminator and the generator. So a generator gets in a random input that is called as a noise, which is basically just used to set the feature values. Since we get this random input into the generator, it produces a bunch of images, which we call as a sample of fake images. We also have some data set of real images, which we can again take a bunch of them and call them as the sample of real images. So the discriminator has basically to take in these two images and tell which one is real and which one is fake. So for the batches of fake images, it will try to produce an output that is as close to zero. And for the sample of real images, it will try to produce an output that is as close to one. That is basically the task of the discriminator. But what generator wants is that the sample of fake images will try to fool the discriminator so that it gets the output as close to one. So just looking at the discriminator part, what we want is for the discriminator, what it wants is that the sample of real images are discriminated to show that it is one, that is a real image, and the sample of fake images are classified as zero, so that it will tell that it is a fake image. And that is basically the discriminator loss. For the discriminator loss function, we have to basically look at the differences between the actual output and the predicted output. So we will go through these in detail in the hands-on lab, but right now we will look at the inner working of what the discriminator does. So first it takes in the image. So this is a 32 cross 32 by 3, basically RGB channels if you want. And these are passed through the convolutional layers so that it gets smaller with more number of filters, passed through another convolutional filter, and then another convolutional filter, till finally you get a single valued output. So this single valued output is lying between anywhere from the range of 0 to 1. So the value of 0 indicates that the discriminator thought that it was a fake image, and the output close to 1 means that the discriminator thought that the input image, which is this one, is actually real. So this is the basic inner working of the discriminators. There are 4 convolutional layers, and we will just briefly see what a convolutional layer means. So as you can see, let's suppose that this block is basically our image that is of size 6 cross 6 and has no channel. So it's basically just a single channel, single width. And this is our kernel, or also called as filter. So what it does is basically it maps onto the pixels and is basically used so that the values are multiplied to each other. So 7 is multiplied with 0, 6 is multiplied with -1, 5 is multiplied with 0, and all of these are added up so that the final output is based on whatever we get here. So this is basically the convolutional layer. So in the case where the padding is not the same, we will start to get images that are smaller and smaller throughout the iteration. So here it is 6 cross 6, but if the padding was valid, so it will be some output that is of lower dimensions. And that's how, as we saw in the previous slide, that the 32 cross 32 image is basically converted into an image that is of size 1 cross 1 cross 1, which is basically a single valued output. And then coming on to the generator part. So for the generator, what it basically wants is that getting some random input, it tries to generate a batch of fake images. And from these fake images, It wants that the generator basically wants that the output of the discriminator is as close to 1 as possible. And the discriminator's part, as we saw, is to basically give the output as close to 0 as possible. So that is the case where the adversary comes in, that the generator wants its images to be as close as 1, and the discriminator wants the images of the generator to be as close as 0. So the generator loss which is computed is backpropagated through the discriminator as well as the generator, which I basically said that this backpropagation is what tells the generator about the changes that it has to make to generate the samples throughout the iterations better and better. So how I explained in the previous few slides that generating the denomination with a face would be a better thing to do. This information is basically passed through this backpropagation. So generator is also a convolutional model, but in this case, the transpose convolutions is used. So initially, we take the input as a value of 100 noise, or we can say that the z value is a vector of 100 different values which are randomly initialized. It is passed, it is basically projected and reshaped into this batch and passed through the transpose convolutional network so that finally we get an image. So it's basically opposite of what the discriminator does. Discriminator takes in an image and generates a single valued output. Generator takes in a random initialized noise vector and then tries to generate an image from it. So finally we get an image through the generator, and we can call this as G of Z, since Z is the noise vector that we have started with initialization. So G of Z is basically the generated image. So the transpose convolutional layer is basically working opposite of how the normal convolutional layer works. So we can see this through this. Suppose that the input is a 2 by 2 image, and the kernel is also kernel, which is the filter, is also a 2 cross 2 of size 2 cross 2. So we will get an output that is basically the kernel will be placed on each of these values, and each of those values are multiplied together. So for first, each of those values are multiplied by 0. Each value of kernel is multiplied by 0, so we get completely 0. Then the value of 1 is multiplied here, so we get as same as the kernel values. The value of 2 is multiplied, so we get 0, 2, 4, and 6. And finally, the value of 3 is multiplied by the kernel values, so we get 0, 3, 6, and 9. And these all are added up together so that we get this output of size 3 cross 3. And that's how we saw that the values of 4 cross 4 or 8 cross 8 are basically increasing and increasing in size. So our input image or our input noise is basically converted into a high dimensional output. And this is the main part of the GANs. This might look a bit worrisome, and it might be looking at this at first might seem difficult and you can't make sense of it. But as we go through this, you can see that it's very easy to understand. So we can start at the discriminator. So what discriminator wants is that the real images are as close to 1 as possible and the fake images are as close to 0 as possible. So when we take the logarithm of this, so the d of x is basically the discriminator that takes in the real image. So when this value is as close to 1 as possible, we get the logarithm of this value as close to 0 as possible. So for the discriminator loss of real values, it will be as close to 0, or it wants it to be as close to 0 as possible. For the fake values, which is basically the discriminator of the fake images, as we know that G of Z is basically the fake generated image. So we want this value to be as close to 0 as possible, so that 1 minus 0 is basically log of 1, which makes this whole thing close to as 0 as possible. And these both values are added up so that the discriminator loss is basically the loss of the real images plus the loss of the fake images. You can average them out by 2 if you want, but that's how it is written, that it is a logarithm of the discriminated values of the real images plus log of 1 minus discriminated values of the fake images. So for this, the discriminator has two basic values for the real image and for the fake image. And for the generator, what we want is that this value should be minimized. It is the same as what is the loss for the fake images, but it varies depending on whether we want to increase or decrease this loss function. So on the next slide, this is basically from the actual algorithm of the DC GANs that we will be using. So we can see that we want to update the discriminator by ascending a stochastic gradient. What it means is that we want to maximize this value. So we want that this value should be maximized so that the loss function of this discriminator makes the values of t of x as close to 1 as possible and t of g of z as close to 0 as possible. And in the other case, for the generator, we want the generator to minimize this loss function so that the d of g of z is as close to 1 as possible, so that as we go towards the logarithm values of nearly 0, we will start to get the negative values. And since we want to minimize those negative values even further, we will have to basically try to increase this d of g of z. So it means that the generator wants the discriminator to output as close to 1 as possible, and in the case of the discriminator, it wants to output as close to 0 as possible. So this is basically those loss functions that I've mentioned here. I will be sharing these slides with you, or the team will share these slides through the mails, and you can refer this as well. So once again, going through the generator loss, we want to minimize this. So it is the most important thing that you have to learn, because the rest of the code is actually easy. And so even without the log, you can just look at this 1 minus t, and you will know that to minimize this, you have to increase this value. So to increase this value, what you want is that the discriminator should output the generated images as close as 1 as possible, as close to 1 as possible. And in case of the discriminator loss, the x of I is basically the real images, the sample of real images, and g of z of I is the sample of fake images. So for this to maximize, we want the value of the discriminated real images to be as close to 1 as possible, and for these images, it has to be as close to 0 as possible, so that finally 1 minus t can be the maximum value it can have. So connecting the whole network together, we can see the full generative adversarial networks working. So what we start with is some input noise, and the generators turn this input noise into some fake data, which is in our case, the images, and we try to fool the discriminator. So X of fake is basically the set of generated fake images. X of real is the set of real images that we already have. So the discriminator's work is to basically try to distinguish between whether the images that are inputted are fake or real. So that's the whole working of GANs. It's just the two main things are the discriminator and the generator. The discriminator has to differentiate or distinguish between the fake and real images, and the generator has to generate the fake images as close to real as possible. That's the main thing of generative adversarial networks. So for our hands-on lab today, we will be going through this MNIST dataset, which is a handwritten digit recognition. But instead of recognizing or classifying these digits, we will be trying to sample some real data, and then using our generator, we will try to generate these handwritten digits. And right now, this might seem like trivial work, but it is basically the same foundation that we can use for generating, let's say, celebrity images or some photos or silhouettes of people which does not exist in real life. It is basically the same process wherein the data set just changes. So what we'll be going through in this lab is basically the same for each and every deep convolutional GANs, and the only thing that needs to be changed is the input data as well as the sample sets. The rest of the code for the generator and the rest of the code for the discriminator will stay the same. So as you can see that the sample image of from the training data is as good as real, which, and the latent sample, which is basically the noise vector, is passed to the generator to sample some fake data. And the job of the discriminator is to either classify them as fake, which is 0, or to classify them as real, which is 1. So putting it all together for going through the lab, we will be first installing some dependencies and load the data set. We will create or define the models. We will initialize those models with some random weights. We will then train those models for at least one epoch while we are going through this hands-on lab. And we'll also try to visualize the results of how it gets better and better, how the generator starts to generate images that are as close to real as possible through the epochs. So I guess we can switch on to the hands-on collab. I think the link will be shared to you guys, but in case it's not, I think the team will share it with you on Google Meet. So, okay, firstly, I am seeing some questions right here. So, ask is what is the input given to the generator? So, basically, the input to the generator is a set of random values which are also called as noise vector or feature vectors. So in our case, it's just random 100 values that are inputted so that it is used in the case that we will get a generated image which is as close to the real image as possible. So changing those input to the generator will define what the output is. So suppose there's a feature vector that is basically used to generate the digit 1, and changing some of those feature vector values will lead to the change in output, so that you might get a digit 2 or digit 3 or something else. So according to it, for our case, it is just the digits. But suppose in the case of generating images of person, those feature vectors can mean that some certain values would be linked to, let's say, the hair length. So increasing a certain value would mean that generating the image of a person would with a longer hair, increase or decreasing the value will mean that you will start to go bald. And these are basically the random feature vectors which throughout the training will get associated with some of the features that we want to generate. And Afreen asks, so how large does the training data have to be in comparison with the sample? So the more the training data you have, the more variety you will get. So there's no limit to how much training data you should have, but you can even work with single digits. So even if you have 10 images from digit 0 to 9, that's enough training data for the GANs to learn. But since it is learning only on those values, it will be difficult for the training data to or for the generated image to have some variety. It will always try to generate those images which are as close to the data set as possible. So given that we want to have some kind of variety in our handwritten digits, it will be better to have some training data that contains a lot of other things. So I think I will start with the GANs. The team has already given you the link. So I will start presenting, and you guys can also have it side by side so that we'll go through this lab as hands-on. So I hope you guys can see this collab, and the first thing I would like you guys to do is to make sure that you go into edit and you clear all the outputs if it's not already cleared. And then go to the runtime tab, change the runtime type, and use the hardware accelerator as GPU. So that while training this network, it will be much faster on using the hardware accelerator as GPU. So I will say that this is the best thing that you could have. So please just change the hardware accelerator to GPU and click on save. And if it's not already connected, you can click here to connect. It will start allocating those resources and it will start connecting to the compute engine so that we can start training online. It will take a while. It is initializing for me, and I hope that you guys are following on and doing it side by side. So make sure that your runtime is set to GPU, and if you want to clear all outputs, you can just go to edit and click on clear all outputs. And then we can start with this digit generation using deep convolutional GANs. So the first thing we would like to do is to import the libraries and load the main data. So since we will be using TensorBoard-X for visualizing the data, we will start by installing this by the by clicking the play button so that it runs just this one cell and it will start to download those library files and start installing it.
Guys, some of you may get an error saying that it is not authorized by Sachin Wani. So you can click run anyway for it since it's shared with you.
Sure, yeah, you can always click on run anyway. And I think it will make a copy of this Python file in your own drive and make sure that you have set your runtime to GPU and you have cleared all outputs just in case. And once these libraries are installed, we will now import the required libraries and the data set that we want. So we will just download our files using GDOM. So I have uploaded the required asset files on this URL so that it automatically downloads. And as you can see in this folder, this we have is that assets.zip file. And once we unzip the contents of asset files, you'll see that it basically contains three files, which is basically the interpolation.gif, transitions.gif, and utils.py. So we'll be using our utils.py file because it contains certain libraries that we will be using, like the logger file, which is used for displaying the results while training. And if you just see here again on the folder, we can see that these three files have been extracted, and make sure that you have these three files visible and all of these cells have been running properly, and you can see this output, and then start to load the libraries that we want. It will take a while, but as you can see that you can ignore this warning because it is just the deprecated function of pandas. But now we can get on to the loading and transforming the data part. So we will mention that we will start with the defining a function of MNIST data that will compose or transform those images into the size that we want. So we resize the images, convert them to tensor, which is basically used for our Pytorch training, and then normalize our values, image values to be between -1 and 1, so that all those pixels values from 0 to 255 will be normalized so that it is between -1 to +1. And we have this out directory that will put in the data, and we will finally return the MNIST dataset. So you guys can run this cell, and since this is just the definition of the function, we will actually run the function in the cell block just below it, and it will start downloading the actual data set and extract it. And if you guys can see that it has extracted, processing, and done, so that you will know that it has been completed properly. You can just click on the contents and then again go to files to see if there is a directory called torch underscore data. And if you could see this, it means that the dataset that we wanted has been extracted properly, and we can move on to the next cells. So the data which we have downloaded is basically a set of handwritten digits, which are all the digits from 0 to 9. And since like Afreen mentioned in the chats that how big a data set should be, we could just use the first row of data set, but using just the first row, we would be generating just images that are as close to this set as possible. But given that in each column there's a lot of varieties about the uh, digits, the generator will learn that there are various possible interpretations. Like the digit 7 can be a normal strike, or there might be a strike through it, so that this also counts as 7, as well as these and other things also count as the digit 7. So when we will try to generate our images, it will start generating images that might look like similar to this, as well as it might look something as similar to this. So this is the data sample, and now we will create the main generative adversarial network functions. That will we will define our generator and we will define our discriminator. Like we saw in the slides, these are the basic sample data set which we have from the training data, and we will use the noise vector to generate some fake data, and the discriminator's work is to discriminate whether it's real or fake. So starting with the generator class, I think it will be better if I zoomed in a little so that you guys can see it properly. So defining the initialization function is basically we are defining various layers. So as we have seen in the slides, for the generator, you will take an input of noise of 100 values, we will project and reshape them, and then we will use 4 convolutional layers to finally get an output of 64 by 64 image. So in our GANs, we will first use a linear function that will take input of 100 and give an output of 1024 into 4 cross 4. So using this, we will then use the first transpose layer, which will take in these inputs of 1024 channels and output them into 5 and 2 using the kernel size of 4, which is basically the filter size of 4 by 4. Stride is equals to 2, padding is equals to 1, and not using any bias. So this will act as the first convolutional layer where we are normalizing and using the ReLU activation function to break the linearity. So similar to this, we also have the second convolutional layer that is also taking in the input as 512 and giving the output as 256 with the same values, the same batch normalization, and the ReLU. The same is repeated for the third time, and for the fourth time we are just using the input channels as 128, giving the output channel as 1, since it is a black and white image that we are working on, so there's no need of 3 RGB channels. The kernel size and the stride and the padding remains the same, but finally there's no ReLU that we use. Instead, we will apply a tanh function that will get our outputs in the range of -1 to 1, since our original data set has been already normalized so that the pixel values are between -1 and 1. So we have just defined these convolutional layers here, and we will finally stack them up using our Pytorch functions so that it starts with the x values. It uses each one of these layers and stacks them up. So we have the linear function followed by the convolutional 1, convolutional 2, convolutional 3, and 4, and finally we'll apply the tanh function, which is the self.out function, and we will finally return the output, that is the generated image. So we will run this cell. Don't forget to run this cell. And it is just the definition right now. We haven't actually ran the function. So we have just run the code cells for the definition. And since someone asked that what is the input to the noise vector, so input to the generator, it's basically the noise vector that is used as a creator using some random numbers. So using the noise function, we've taken the size and generate a batch. So size is basically the batch size, and we will use a variable which is a random number, random, which is of shape size by 100. So each of those images will have some 100 random values to it. This torch.cuda is basically used for using our runtime as GPU. So if we have the GPU available, it will return the GPU variant of those variables, or it will just return the random variable. So you might get this warning that you are not connected to a GPU runtime. You are connected to a GPU runtime, but not utilizing the GPU. Just ignore this warning, because during the end of the function, we will actually be using the GPU runtime. So just run this cell as well. And then we can come on to the discriminator class. So the discriminator class is basically a simple classifier that takes in an image, applies some convolutional layers, and then finally decides whether the image is real or fake. As we have seen in this, it will take some kind of image input, apply some convolutional layers, and finally get a single valued output. So for our case, we will start with the first convolutional layer that will take in an input image of some size with channels equals to 1, that is a black and white image, and output channels equals to 128 with all those kernel size, stride, and padding. We will use leaky relu as our activation function in this case. In the second convolutional layer, we will again take this output of 128 and apply the out channels to 256. So this will go through and go through so that our images will get smaller and smaller, but our number of channels, that is the width, will keep on increasing. So the 256 is now converted into 512 in the third convolutional layer, and in the fourth convolutional layer, the 512 value is converted to 1024. And since we already have those output as 1024 into 4 cross 4, so we will apply a linear function that takes in all these values and just gives out a single valued output. And then we will apply a sigmoid function to get our outputs in the range of 0 to 1, so that if the value is close to 0, we will know that it is a fake image, and if it is close to 1, we will know that it is a real image according to the discriminator. So as same, we have just defined the functions here, and we will stack them using this forward function. We'll start with the first convolutional layer, second, third, and fourth, and then finally we will apply a sigmoid function to get the output between 0 and 1. So make sure that you run this cell as well, and then we can finally come on to initializing our weights. So to initialize our weights, we are basically using some normal values, and those weights are uh, initialized between these range so that there are small values which prevents some problems like gradient explosion. So we'll just define our initializing weights function here, and we can finally create the instance of our network class. Since we have defined the generator and the discriminator as a class, we will instantiate an object called generator and an object called as discriminator using the generative net class and the discriminative net class. We will apply the init weight function so that the weights of those generators and the discriminators are applied. And finally, if the CUDA is available, basically is to train faster using a GPU, we will convert that generator into a CUDA and discriminator so that it runs well with CUDA functions. That is the GPU. So we will also run this cell. It might take some time to apply the initialization weights. but it won't take more than a minute. Okay, so it's already done. So as you can see, so we will now visualize the model using summary. So for someone who is well versed with Keras, you guys know that using just model.summary function works well with any model in Keras. But in case of Pytorch, we have to install a torch summary library, and from that we will have to pass in the model as well as whatever is the input size to the model. So for the generator, we will if we just run this function, I think that torch summary is already installed, but as a precaution, I'm just putting it here, and we will finally get this summary. So from this, you can see that for the generator, we will be giving in the random noise from which the various convolutional transpose networks are passed through, whereas there's batch normalization and ReLU. Then again, the next convolutional layer, the third convolutional layer, the final convolutional layer, and then we finally apply tan so that our values of 1 cross 64 cross 64, all these pixel values are within the range of -1 to 1. The first value, -1, of all of these indicates that the batch size can be variable. So for our case, we are using a batch size of 100, but depending on the data set, since it can vary, so it always shows that the first dimension is -1, and the rest of the dimension, this is the output channels. So one is for the black and white images. It will be 3 for images that are generated as red, green, and blue. This is the width of the image, and this is the final generated height. So as we can see that the total number of parameters that we are training is close to 12 million parameters, and it is a significantly big model. And as you can see that the total estimated size of the model is around 53 megabytes just for the generator. So it will be similar to for the discriminator, where we will input the image of size 1 cross 64 cross 64, which means a black and white image of size 64 cross 64. We will run this and we will get this output. So using the convolutional layers, we are applying the first convolutional layer, the second one, the third one, and the fourth one before we apply the linear transformation and then the sigmoid. So the linear is basically the fully connected layer of, or the dense layer in Keras. So these values will all be connected to a single output, and this single output is then finally passed to the sigmoid layer, so that the outputs that we get are within the range of 0 to 1. So as same as in the generator, this -1 indicates the number of batch size, which can vary. And this final output of 1 means that it will be a single valued output, like we have seen here, that it is a output of just size 1. So it also has a size of around 50 MB. So adding both of these, our total size of the model is around 100 megabytes. So all its weights when trained, the model will be of size of 100 megabytes. So we will finally come on to the training part. So we will use the Adam optimizers for training, and we will pass in those parameters of the discriminator, use the learning rate as a small value, and we will set these beta values, which is intrinsic to the Adam uh, optimizer, to be 0.5 and 0.999. So same as the discriminator, we will do the same with the generator, where we will pass in the generator parameters. We will use the binary cross entropy loss as our loss function, since it is only that we are discriminating between 0 and 1, so that is a real image or a fake image. So the binary cross entropy loss works fine. And for the number of epochs, we are setting it to 1 right now, since it's a hands-on lab, because training even one iteration will take some time. But if you have a good enough GPU at your home, or if you want to keep running this Colab for a long time, you can change it to 200 after this lab ends. So we can just run this optimization function, and then finally we will create the target data, that is the labels. So since I have said that the real data's label will have value is equals to 1, it means that for discriminator to show that it's a true image, we have to compare the output of the discriminator with the output of the real data label, which is equals to 1. So we will just generate a variable which is just a value of ones of size of the batch size, comma 1. So it will be basically an array of size equals to size, and it will be all be filled by 1. So you can see that it is just an array of 1, 1, 1 continuing on, so that its size is equals to the batch size. And for the fake data, the label will have the value of 0 for the discriminator to show that it is a generated image. So since it is 0, we will use the torch.zeros function to create a similar array, but this time it will be an array of just size equals to the batch size, but values will be 0. And this, as said, that this CUDA functions is basically used when we have the GPU available, so that the initialization and the working with the data set is faster. As it is a tensor, it can also work on the tensor processing units. So we'll just run this cell. And then finally, coming on to the most important function, is that encapsulating the training functions for generator and discriminator, and finally defining our loss function. So this function train discriminator takes in the generator optimizer, the real data as well as the fake data. So we will just reset our gradients. We will take the prediction of the real value by passing in the real data to the discriminator. So this will basically give us an output, a single valued output, which should be close to 1. So the error function is basically defined as the loss between the whatever value we have and comparing it with the real data target. So real data target, as you remember, is this function that is basically an arrays of ones. So this loss function will compare the value of the real prediction with the value of 1. So if it's as close to 1 as possible, the loss function will be low. And if it's far away from 1, the loss function will be high. And we will propagate this loss function backwards to make the changes. So same with training on the fake data. We will just get a fake prediction using the discriminator passing in the fake data. We will then again compute the fake loss, which is basically comparing the prediction of fake image with the fake data target, which is just a bunch of arrays that is valued at 0. So if the fake prediction is close to 0, the loss will be less. And if it is closer to, or it is higher values, then the loss function will be more. We'll again pass it backward. We will update it using the optimizer.step. And since this is a function that we haven't yet run, we will just return all these values which can be used while final training. So we will return in the sum of real and fake errors. We'll also pass in the predicted real output and the predicted fake output. And this is just a 0, 0, 0 in case that the first time the value has not been initialized, so that we don't get an error. The same is with the train generator, but instead of having two different errors in this case, it is just a prediction of passing in the fake data to the discriminator. And in this case, we are basically comparing the loss function of the fake prediction with the real data target. Basically, what this means is that the generator wants the prediction to be as close to 1 as possible. You can see the discrepancy here that in case of the discriminator, We are comparing the fake prediction with the fake data target, which is basically predicting with comparing it with zeros, as we have written here in the comment that we are comparing it with the fakes with zeros. And in this case, we will be comparing it with the real data target, so that we are comparing it with the values of 1. We'll pass it backward, update the gradients, and return the error. So make sure that you run this cell, and we will move on to the next test, which is basically generating the samples. So since I mentioned that we will be using a batch size, so here the batch size is 16. So whatever is there's minus ones here will be replaced by 16. And since it is a variable, that's why it has been mentioned as minus one in the summary. But in our case, we will use a sample size of 16. So we will just generate those noise vectors as well. And then this function will take the longest time to run, but it is basically running for each epoch in range number of epochs. And if you have set this number of epochs to 1, we will be training this for one epoch, and for each of those epochs, we will be training the discriminator. If the CUDA is available, then we will generate some fake data. We will take the error functions, and we will also just append them so that we can plot a graph through the iterations as it gets better. And same with the train generator, where we will generate the fake data from the noise function and pass in through the generator. We will then compare this with the function and then get the loss and append them to the loss list. We'll also use logger.log, which is helpful to log our errors. And through the display progress, this is just a function that is used to plot some images throughout the training. So it's something that you don't have to worry about. It's just normal plotting functions using Seaborn or Matplotlib. So it is not really important for this step. It is just to show how the training is working. And we will be saving our models through each epoch, so that in case that if you want to run this model, say for 20 epochs and then again continue after it, the models will be saved in the files. So we will start running this function first. And as you can see that this will actually take a long time, but just to make sure, you will see that we get the first output as epoch 01, where the batch number is 0 by 600, and the discriminator loss is some positive value, the generator loss is some positive value. We get the discrimination of the real image as this value, and the discrimination of the fake generated image as these values. As you can see that these values are the same, because right now, before any epochs, the discriminator is just initialized with random weights, so it will not know the difference between the real image and the fake image. And as you can see that these batch of 16 images are basically generated by the generator, which hasn't trained on what the real images looks like. So it's just a bunch of pixels that are a bunch of random values. So training this model will take a long time. So while this is training, I will just move back to my presentation, and we will see what is ahead of this. So here are some amazing applications of GANs. So what we are doing right now in those collab is something that you might think that it is trivial, but it is basically the whole code is same for doing each of these works. So in case of face generations, using another data set and using the same model, we will also get a model that can generate some images of persons. In our case, we are using some digit generation because it is the hello world of GANs. But if you want to go deeper, you can even try to generate the face generation. And as we can see that there's this site where we have used some style GANs, and It is a generative adversarial network built by NVIDIA, which is basically working on the same principle, and it generates some images of the person that looks really real, but in reality, this person does not exist. This person has been completely generated by a GAN. And if you look really closely, you can try to find some or the other thing that will make you believe that this is not a real person. As you can see, just towards the lips, there is some problem right here. The microphone that he is holding is not properly generated, since there must not be a lot of examples where there is microphone in the image, but the rest of the image looks pretty clear. And training a model like this takes a lot of time, but the basic code and the basic implementation is the same as what we went through in our collab. So if you just refresh this page, you can even see that it generates some images with even with person having some glasses on them, and it really looks real. And for someone looking at this not so seriously, you cannot differentiate whether this person is real or fake. So I think that you, even as a human acting as a discriminator, cannot differentiate whether this person is real or fake. And you can just keep on refreshing and you will get some generated images each time. And this shows that how well this technology has come forward. It was GANs were basically invented in 2016, and since then it
Just
has
a
been
doubt.
less than 4 years. Yeah, yeah, yes,
When we are trying to refresh that
We'll be
page,
taking the doubts after.
yeah.
when we are trying to refresh this page, is it being generated real time or is it already generated pics which are showing?
Actually, it has been generated already since the model was trained by NVIDIA themselves. They have some repository where those images are already contained, and it is continually updated so that new images are basically generated and put into those repositories. But the images that you see right now are not generated in real time. It has already been generated.
Thank you.
So this was one of the applications of GANs. So if you guys are into gaming, you would know that NVIDIA has used this technique called as DLSS 2.0. So for someone who has some information about gaming, or at least information about screen resolutions, what this DLSS does is that it is using a GAN called as super resolution GANs, so that the images which are basically generated in 1080p can be upscaled to some higher values. So using this, what it does is that you can go through this. Since I will be sharing these slides, you can go through each and every one of these values and sorry, the links, and you can just read them. But using this DLSS, which is basically deep learning super sampling technology, you can generate images that are generated in 1080p and are upscaled to 4K resolution. So just using your normal graphics card, which can run games on 1080p, you can just generate those images or generate those frames in 1080p, and using the deep learning super sampling, you can just upscale them to 4K. So using that, and there are also certain techniques that enhances the details. As you can see in the original image here, there isn't much detail in the word investigation, but using the deep learning super sampling, using the updated one, you can see that the word has been much more detailed. So there are this application of GANs where you can basically take in an image which is of lower resolution and upgrade it to a higher resolution image, as well as increase the details in that image. So this is one of the applications of GANs, and we will just switch back to Colab and see what the training has. Okay, so right now the batch number 100 has been trained, so we are just inside 1/6 of the training done, and we can see that there are some kind of patterns forming in the images. So right now it's still far away from what we want, but you can see that this is trying to generate an image of zeros. This is trying to also look something as close to 6 as possible. But as soon as we start training, it hasn't been even one epoch. So of course it will take a lot of time, but you can see that where it was generating some random noise at the beginning, right now it is trying to find some patterns in the images that it wants to generate. And using these plot functions, we can see that the generator's loss and the discriminator loss will be continually increasing or decreasing. But using this function graph, you can check that neither of the two are just going in the league of their own, so that the generator becomes so good at generating just a single image that the discriminator loss will start on increasing. So that is a bad thing. And on the other hand, if the generator loss starts increasing and the discriminator loss stays the same, it means that the generator is not doing a good job in generating the images. So using this graph, we can check that through the iterations or through the epochs, the loss of the generator and the loss of the discriminator should not vary as much. Since it is an adversarial training network, throughout the iterations, the discriminator gets better as well as the generator gets better. So over time, both of those models will get better on their own, and hence the loss functions will not change. But in case they change, or if one of them gets better and one of them stays the same, it means that we have gone into one of the biggest traps of GANs, which is the mode collapse, or it's just that the generator or the discriminator has become so good at discriminating the images that it has no new information for the generator. So we have to be careful of these, and there are various techniques used in the recent papers that tries to avoid any of those problems. But yeah, while this training happens, let we will switch on to see more applications of GANs.
So we have some doubts in the comment section.
Oh, sure. Uh, okay, so Dark again asks that what does conf 2D and conf 2D do? So in case of the discriminator, the conf 2D function is basically what I have mentioned here in the slides. For the generator, this conf2d, okay, so first for discriminator, we'll see that this conf function takes in a certain image, applies those filters as we have seen, and then generates an image. So this gif that we had shown is basically this is the input image, which in our case is the image of size 64 cross 64, whereas this kernel size is of 4 cross 4, and we will be generating images across various things. So this is basically a convolutional layer which is used to take in the image and then generate the subsequent iterations of it till we finally go to the last single valued point. And for conf transpose, it's just the opposite, that we are starting from here using our kernel function and filling in these values. It's basically the opposite function. So like I said here, the transpose convolution is the conf transpose 2D that we have been using. So in our case, in our case, the kernel was of size 4 cross 4, and the input were basically the noise vectors, and then we were generating those outputs using those noise vectors. And this output through the iterations basically converts into a 64 cross 64 valued output, which is an image. So that is one of the applications. Okay, and so we will be moving on to more applications. So here is the super resolution paper that you can read about how it is using a single image super resolution using GANs. So as you know that in most of the camera applications in your Android phones, there is an option called as super resolution, which is basically taking an image and then using a GANs to upscale it into 4x. So for suppose that if you have an image that is it in a 1080p format, so upscaling it would basically mean that you are taking that image and converting it into 4K. So you can go through this paper and you can download it from PDF or some other formats and you can read through it about how it works. But SR GANs, or called as Super Resolution Generative Adversarial Network, is used for inferring photorealistic natural images. And then there's this another block by NVIDIA that uses the power of GANs so that even a normal person can draw anything. So just drawing this normally, you can see on the right side that the GANs will generate a real image that is as close as real life as possible. So it's basically called as GAN, and it's just used for drawing so that even a normal person or even a beginner can draw these, and you will get some really good real valued outputs. And you can just also read through this and watch some videos about how it is made. And there's also a link to the research paper if you want to read about it. And there's a cool podcast about other things. So most of the works in GANs has been done by NVIDIA. So most of those resources that you will find are also linked to these sites in NVIDIA. But yes, that is one of these applications. So deepfakes is something that the world is getting used to right now. It's you may not be able to hear this right now, but yes. So you can see that deepfakes is basically generating some images. You can say in this case of Obama, while someone else is reading out some statement, and you can see that it feels as real as possible. So as you can see that there's a lot of work that has been going through, and so there's a problem that some people are thinking that in the future we will not be able to use videos or photos as the evidence of proof, because since it is manipulative now, anyone can see anything or anyone can use GANs to do something. So there's this downsides to the technology. Like always, there's some good things and some bad things that always happens. And unfortunately, deepfakes is one of them that is a bad thing, right? So there's also some other applications. And okay, so we can see right now in our page that training it through half the iterations, we start to get some kind of values, but it will take a long time for even one epoch to end. So I have already included some of those uh, results after the training. So as we saw in the epoch 0, it was just bunch of random noise that were generated. Through epoch 10, we will start seeing some kind of patterns, but still it is nowhere near as good as the real images. Through epoch 50, we can finally then see that the images are being generated. We can clearly distinguish that this is a 5910798310335. This looks like a 9 or a 7. This was supposed to be 8, I guess, 4 and 7. So still it is a long way. And I would recommend you guys to run it for around 200 epochs to finally see the results. But it will take a lot of time. So in case that you want to stop it running right now, and if you want to run it later, you can just click on stop button here. or if you guys want to keep it running, you can keep it running. But uh, I have just stopped this right now to show you if you could run these values here as well. So I have basically already trained up till 90 epochs and generated and compiled a GIF out of it. So using this function, we will be able to display that GIF into Colab. So as you can see, after every 3 epochs, I have included one picture. So there's nearly 30 pictures here and contains around 90 epochs. You can see that after epoch 20 or 30, you will start see that the generated digits are legible, and over time it gets better and better and better. And in the beginning, it was just pure random noise, and then it gets better and better. So, as someone had mentioned about how the noise vector works, so consider that for a noise vector of just two inputs, just so that I can explain it better. Consider a noise vector input of just value 1 and 3. So considering this 1 and 3, suppose we get an image that is generated that looks as close as 6, and for other example, let's say 2 and 4 to get the output of 7, we can average those out to see the interpolations in between. So using 1.1, 3.1, 1.2, 3.2 up till 2, 4, we will see the various interpolation values between the output of 6 and the output of 7. So using that, I have also included a cool interpolation GIF that you can see how those digits change when you use those feature vectors and generate the values in between them. So as you can see here, it starts from 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, and back to 0. So it's basically a loop that's happening. And what are the interpolations in between are basically the feature vectors that are kind of weighted averages. So those features basically define what digit is going to be generated or what features the final images will contain, what edges, what lines, or what patterns the image will have. And using those interpolations, we can see this in between. So I will come back into take more questions. So is there a specific reason we use the Adam optimizer? So as you guys know that there are lots of optimizers. There's simple gradient descent, there's RMS prop, and there's momentum. But Adam optimizer, in case of GANs, is used so that, like I said, there's this problem of exploding gradients and other things. So using the Adam optimizer with the beta values set to the values we had mentioned earlier, that is 0.5 for beta 1 and 0.999 for beta 2. These are the tested values that works really well for Adam optimizer in case of the GANs that we are training. So there's not a single specific reason that we have used an Adam optimizer. You can use an RMS prop as well, but these were the tested values. These were tested by a few papers, and the original paper used these same values. So I have just included them. You can just try and experiment with some other optimizer functions and see how it trains. So are there other generative networks as well? So for Samreen, I would say that yes, one of the biggest or the hottest topics right now, the OpenAI's GPT-3 is kind of a generative network. It is a generative pre-trained transformer. So it basically generates your images or text or code or stories based on your inputs of text. So since this was just a generative network used to generate the images, there are a lot of different generative networks that can take in a text and generate some music, take in a text and generate a whole story out of it. So there's a lot of possibilities, and there's a lot and lots of generative networks that has been increasing, still coming out, and has been one of the best or the most hottest topic right now in deep learning. So I think that since this has ended right now, and we have stopped the training for myself, we can see that over the interpolations and through the epochs, the digits just get better and better. And for people that think that this was not something as good as other things, but it is just the hello world of GANs. And if you go deeper into this, you will see a lot of things that are just currently going, and there are a lot of research papers and lots of new contents is being generated. So I would I would suggest you guys to be active into the group, and you just stay with the community, start reading those research papers. It will be great to be well acquainted with these technologies. So, Dr. Sujata Rajkumar asks, how do you measure the accuracy of digit being recognized? So, that is a very great question, and it was one of those problems in the beginning that how, as a computer, can you check that a digit being generated is good or not? Because in the starting as well as in the end, the loss functions do not change as much. So throughout the iterations, we can see that the generator loss and discriminator loss nearly stays the same. So it's just that we can see, or we can actually uh, say that okay, right now this starting it was not a legible digit, and it is getting more and more legible. It is more getting more and more readable. But uh, like I said, this is the hello world of GANs. So there are a lot of different adversarial networks that are called as uh, WGANs, which is using a technique called as Wasserstein loss. So using that Wasserstein loss, or there are multiple other GANs as well, you can measure the accuracy of a digit being recognized. So it's still a topic where we don't have a specific fixed criteria that this is going to work, but there's a lot of research that is going on about measuring the accuracy of digit being recognized. So that was a great question. And how can you apply this model for fake news identification? So we can use the discriminator part, wherein in not in these models, but in the case where it can take an input of text, we can use a discriminator and then pass through some LSTMs or other recurrent neural networks so that we can use this model to apply for some fake news identification. So I think that the fake news identification, instead of GANs, it can be used in case of the discriminator or just some classification. What you can do with GANs is try to generate news. Since it is a generative adversarial network, you can just train them on a lot of news, and it will get better and better, and it will learn how the news is being created, and it can just start creating its own news based on some inputs. So there are some research papers where you just input two or three main words of your choice, and it generates a whole story or the whole news after it. So you can also refer to that. And yes, if anyone has any more questions, they can post it in the chat box. I will be sharing those slides as well as the collab uh, via the team so that if anyone wants it, they can get it. And if you guys have any more questions, you can just post it here.
So, okay, so uh, I would like to thank our speaker, Mr. Sachin Wani, for making time for this webinar amidst this busy schedule. It was very informative and we really enjoyed the hands on session. And special mention to all his colleagues who were also part of this webinar. Thank you for joining us. I would also like to thank everyone who worked behind the scenes for organizing the webinar, and more importantly, a special thanks to all the attendees and the faculties who tuned in for the session. I hope you all found it interesting, and at IoThinC, we conduct many intriguing sessions and events regarding the growing trend of IoT. Follow us on our social handles to stay updated. Once again, thank you, one and all.